In case of macromolecules, let's learn about the chemical bonds, stabilizing forces of biomolecules, bonds which hold biomolecules. In living systems, the stability of biomolecules is maintained by various types of chemical bonds or attraction forces. Chemical bonds are the attraction forces between atoms strong enough to permit the combination of atoms to function as a single unit. These attraction forces range upward from 0 to those which involve more than 250 kilocalorie per mole of the bond. All chemical bonds probably originate with the electrostatic charges on electrons and atomic nuclei. Bonds may result when the net Coulombic interaction have significant attraction forces. Coulombic reactions are the reactions which involve electric charge. Similar charges repel from each other and opposite charges attract each other. The major stabilizing forces present in biomolecules are covalent bonds and non-covalent bonds. So let's learn about the covalent bonds. These are the bonds in which electrons are shared by two atomic nuclei. Thus, a covalent bond is formed when two atoms achieve a stable electronic grouping by sharing a pair of electrons. The bonding electrons are relatively localized in the region of the two nuclei, although some degree of frequent delocalization occurs when the shared electrons have a choice of orbitals. The conventional single covalent bond involves the sharing of two electrons. Double bond has 4 shared electrons and triple bond has 6 shared electrons. Covalent bonds may range from nonpolar to extremely polar levels. In the former, that is the nonpolar case, the bonding electrons are evenly shared by the two atoms. The bonding electrons are evenly shared by the two atoms, but in the later, that is the polar case, they are very unevenly shared. The limit of uneven sharing occurs when the bonding electrons remains with one of the atoms throughout. The limit of uneven sharing occurs when the bonding electron remains with one of the atoms throughout. This makes that atom a negative ion, leaving the other atom as a positive ion. Ester bonds in nucleic acids, peptide bonds, and disulfide bonds in proteins, glycosidic bonds are example. Wait a minute. The limit of uneven sharing occurs when the bonding electrons remains with one of the atoms throughout. This makes that atom a negative ion, leaving the other atom as a positive ion. Ester bonds in nucleic acids, peptide or amide bonds in and disulfide bonds in proteins, glycosidic bonds in complete carbohydrate, etc. are covalent bonds. Covalent bonds are strong bonds in the sense that the energy required to break such a bond may be in the range 150 to 450 kilojoule per mole. Atom 1, atom 2 electron. Covalent bonding, electron sharing, shared electrons can be seen. Covalent bonding due to sharing of electrons between two atoms. First, we will be drawing a circle, and that we will be putting an electron along with another atom as a circle, and then the electron in that. Electrons are negatively charged. So first, we will be labeling the first first circle as an atom 1, next one is an atom 2, and then we will be showing a combination sign. And then we have to draw it in a different way, like these two circles are joining and the middle portions are connected by showing the two shared electrons in between them. So by this way we can represent the covalent bond. Okay, so that is what we can see from the graph. Next stabilizing interaction is the non-covalent interactions in and among biomolecules. Biomolecules assume a characteristic conformation. So, non-covalent interactions in and among biomolecules. Biomolecules assume characteristic conformations or interact with one another primarily through non-covalent interactions. Several of these forces are individually weak and non-specific. However, they are significant in producing complex macromolecular structures in specific. They are weak and non-specific. However, they are significant in producing complex macromolecular structures in stabilizing the transition states of biochemical reactions, in passing sophisticated messages, etc. Thus, they play key roles in the replication of DNA, folding of proteins into three-dimensional forms, recognition of specific substrates by enzymes, and the detection of signal molecules. They play key roles in the replication of DNA, folding of proteins into three-dimensional forms, recognition of specific substrates by enzymes, and the detection of signal molecules. Non-covalent interaction can be intramolecular within the same molecule or intermolecular between different molecules. Non-covalent interaction can be intramolecular within the molecules, within the same molecule, or intermolecular between different molecules. The common non-covalent forces include electrostatic or ionic bonds, hydrogen bonds, hydrophobic interactions, van der Waals interactions, etc. Ionic bonds or electrostatic bonds. Ionic bond, electrostatic bond, or electrovalent bond is a force of electrostatic attraction that holds together oppositely charged ions which are formed by the transfer of one or more electrons between atoms. During the formation of an ionic bond, one atom donates an electron to another atom. As a result, the electron donor becomes positively charged and the electron acceptor becomes negatively charged. Thus, a strong electrostatic attraction is established with high melting temperature. They may be really readily soluble in water and other polar crystals. A strong electrostatic attraction is established between them, forming an ionic bond. Compounds bearing ionic bonds are mostly crystalline with high melting temperature. They may be readily soluble in water and other polar solvents and are capable of conducting electricity. Ionic bond containing compounds are mostly crystalline and with high melting temperature. There will be a high melting temperature. They are readily soluble in water. They can be easily solubilized, and what in case of water and other polar solvents, and is capable of conducting electricity also. That is the peculiarity of ionic bonds or electrostatic bonds. So for example, here we can see Na plus along with the Cl minus, and they are combining together by forming an ionic bond. The Na plus and Cl minus ions thus formed are then held together by electrostatic forces of attraction to yield the ionic compound sodium chloride. In solid ionic compounds, the ionic bonds electrostatic attraction forces are very strong. However, the aqueous solutions, these compounds dissociate into oppositely charged ions because water has a very high dielectric constant D. Here we can see in solid ionic compounds, we are taking the case of solid ionic compounds. The ionic bonds electrostatic attraction forces are very strong. However, in aqueous solutions, these compounds dissociate into oppositely charged ions because water has a very high dielectric constant, and therefore it is capable of reducing the attraction forces between the ions to separate them. The force F of an electrostatic attraction between the ions is given by the Coulomb's law. F is equal to Q1 Q2 by R square D, where Q1 and Q2 are the charges on the ions. R is the distance between them and D is the dielectric constant of the medium. Obviously, for a given pair of oppositely charged ions, the attraction is the strongest in vacuum, where D is 1 and the ions are closer. On the other hand, the attraction would be very weak in a medium of high dielectric constant such as water, where D is equal to 80, where the ions are well separated. R is the large. Electrostatic interactions are very important in bringing about biochemical reactions and also in stabilizing the structure of biomolecules. A charged group on a substrate can attract an oppositely charged group on an enzyme and thereby facilitate an enzymatic reaction. The same kind of attraction may facilitate bonding between two different oppositely charged molecular entities in heteroproteins. The bonding between the negatively charged nucleic acid entity and the positively charged basic protein entity in a nucleoprotein. What is happening? The same kind of attraction may facilitate bonding between two different oppositely charged molecular entities in heteroproteins. The bonding between the negatively charged nucleic acid entity and the positively charged basic protein entity in nucleoprotein. So that is what we can learn from ionic bonds. So the next one is the salt bridges. Salt bridges are weak ionic bonds formed between positively charged amino acids. This is a kind of weak ionic bond between positively charged amino acids like arginine, lysine, and negatively charged amino acid, aspartic acid, glutamic acid. Next, let's learn about the bridge bonds. Bridge bonds, these are the bonds which involve the compounds of hydrogen, in which the hydrogen bears either positive or negative charge. When a hydrogen atom is attracted to a molecule by a polar covalent bond, it may attract another molecule, bridging the two molecules close to each other. What is happening? When a hydrogen atom is attracted to a molecule by a polar covalent bond, it may attract another molecule, bridging the two molecules close to each other. If this hydrogen is positively charged, it may attract an electron pair of the other molecule. This is called protonic bridge. If the hydrogen is negatively charged, it may attract the nucleus of an atom of another molecule through a vacant orbit. This is called hydridic bridge. What is bridge bonds? These are the bonds which involve the compounds of hydrogen in which the hydrogen bears either positive or negative charge. When a hydrogen atom is attached to a molecule by a polar covalent bond, it may attract another molecule, bridging the two molecules close to each other. If this hydrogen is positively charged, it may attract an electron pair of the other molecule. This is called protonic bridge. If the hydrogen is negatively charged, if the hydrogen is negatively charged, it may attract a nucleus of an atom of another molecule through a vacant orbital. This is called hydridic bridge. Hydridic bridges have only very low bond strength. Still then their effect on the physical properties of the condensed state of the substances in which they occur is very significant. Hydrogen bond is an example of bridge bonding. Hydrogen bond is an attraction force. Hydrogen bond is an attraction force or a bridge in polar compounds such as water. It is a hydrogen atom of one molecule is attracted to two unshared electrons of another molecule. The hydrogen atom is the positive end of the polar molecule and it forms a linkage with the electronegative end of the another such molecule. This can be represented by the following formula in which the central hydrogen atom forms the bridge. Hydrogen bonds are commonly found in compounds which contain strongly electronegative atoms such as NO and F. They are important in the bonding of cellulosic compounds, base pairing on DNA, etc. Hydrogen bond is formed when a hydrogen atom remains sandwiched between two electrophilic electron attracting atoms, usually O and N. It is significant in stabilizing. Suppose a hydrogen atom is covalently bonded to a strongly electronegative atom like F, O, or N, then the bonding electrons are displaced towards the more electronegative atom. As a result, a partial charge separation occurs and the molecule becomes polar. In other words, the molecule become a dipole with the hydrogen end having a partial positive charge and the other end having a partial negative charge, and this is shown by HF and H2O molecule. Hydrogen bonding creates polar molecules, dipoles. A hydrogen atom linked covalently to a highly electronegative atom like F, O, and N may get additionally bound by dipole-dipole attraction force to another highly electronegative atom of the same or a different molecule. This relatively weak attraction force is a hydrogen bond. In some cases, the positive hydrogen end of a molecule interact with the negative end of a neighboring molecule or with the neighboring part of the same molecule, forming a bridge between them. It is this special case of dipole-dipole attraction that is called hydrogen bond. Hydrogen bonds are much weaker than covalent bonds but stronger than the ordinary intermolecular force called van der Waals forces. So in some cases, the positive hydrogen end of a molecule interact with the negative end of a neighboring molecule or with a neighboring part of the same molecule, forming a bridge between them. It is the special case of dipole-dipole attraction that is called a hydrogen bond. Hydrogen bonds are much weaker than covalent bonds but stronger than the ordinary intermolecular forces called van der Waals forces. They are only 1/10 to 1/13 as strong as covalent bonds. Still, they have significant effect on the properties of the substances in which they occur, especially with regard to the melting and boiling point and the crystal structure. There are two types of hydrogen bonding, intermolecular and intramolecular. So, which is the strongest one is the covalent bond. Next is the hydrogen bond, then the van der Waals forces. The next category of hydrogen bonding or the next two type of hydrogen bonding can be seen. The first one is the intermolecular hydrogen bonding. This is the hydrogen bonding between the different molecules of the same substance or between different substances. Intermolecular hydrogen bonding causes the association of molecules into clusters. An example is the association through intermolecular hydrogen bonding in HF. Hydrogen bonding is usually shown by dashed lines. Intermolecular hydrogen bonding. So water is another compound that shows association through extensive hydrogen bonding. This is for this reason that water shows some unique properties which are vital to the very existence of living organisms. Organic compounds containing the groups OH, COOH, NH2, etc. often exist as associated molecules by intermolecular hydrogen bonding. Such compounds can also enter into hydrogen bonding with each other and also with water. Intermolecular hydrogen bonding. Intramolecular hydrogen bonding. This is the hydrogen bonding within the same molecule. Intramolecular hydrogen bonding in salicylic acid, orthonitrophenol, etc. Both intermolecular and intramolecular types of hydrogen bonding are common among many biologically important